Hello, everyone. Welcome to the Optics Valley Monthly Technical Series. Optics Valley is a committee of the Arizona Technology Council and one of the world's leading clusters for optics, photonics, and astronomy in the world. Our speaker today is Bob Parks, president of Optical Perspectives Group. Bob received a bachelor's and a master's in physics from Ohio Wesleyan University and Williams College, respectively. He then worked as an optical engineer at Eastman Kodak Company and iTech Corporation prior to gaining optical fabrication experience at Frank Cook. In 1976, he went to the Optical Sciences Center at the University of Arizona as manager of the optical shop. Subsequently, he was promoted to assistant research professor. And in 1992, he started Optical Perspectives Group along with Bill Kuhn. Currently, he continues to operate Optical Perspectives Group as sole proprietor. Special thanks to Optical Perspectives Group for sponsoring today's presentation. Welcome, Bill. The floor is yours. Welcome, Bob. Excuse me. Floor is yours, Bob.
Thank you for the introduction, and I'm delighted to be here to talk about this business of alignment with Bessel beams. At the very beginning, though, I think there's a polling question for you, just to ask if you are familiar with autocollimators and alignment telescopes. I already know from the list of attendees that most of you are, but this will help me sort of guide the presentation. But even looking at the attendees, it got me thinking, why are there as many people as there are attending this if you're completely happy with using classical techniques for alignment? The very fact that you're here sort of gives me a clue that if things could be made easier, you'd be happy about that. So okay, we've got some answers here. It looks like most of the people are familiar with this equipment, so we can go right on. With what I'd like to do is sort of an outline, define what I think of as alignment in general, look at classical instruments a little bit, and then go into some past efforts to improve alignment, talk about Bessel beams, and then give you some examples of using them. So my definition of alignment is just getting a third point on a line that's defined by two other points, except in the case of optical alignment, you not only have to get your lens, and I don't know which screen you can see my pointer on. You see the pointer?
We do now. Yep, we see it there, Bob.
Okay. Yeah, you not only have to get the lens on the line joining the object and image, but you have to get the axis of your optical system on your line of sight. And if you only get the lens on there without worrying about angle, you get the image back on the line of sight, but it's going to be a fuzzy image because of tilt in the lens, or you get aberrations. So the optical axis of your lens system has got to be coincident with the line of sight. And this means your optical system axis must be aligned to the line of sight in 5 degrees of freedom, 2 tilts, 2 displacements, and then focus. This gives a little bit of an idea here. I'm just, again, using single lens as analog of your optical system, but the optical axis of that system is defined by the line joining the centers of curvature of the two surfaces of the system. And you want that optical axis to be coincident with the line joining your object and image. When that is the case, then your finite object is imaged on the line of sight, and rays coming from infinity will also end up on this line joining object and image, as well as the optical axis of your lens system. But there's some practical difficulties with this, mainly that you can't touch centers of curvature or optical axes. The other thing is, of course, your optics themselves have mass and form, and so they are mechanical. They are things you have to touch, and so you need optical instruments or rotary tables to help do the alignment. I'm going to talk briefly about autostigmatic microscopes, but they come to a focus and so only give you information about 3 degrees of freedom and cannot sense angle. Alignment telescopes do talk about I call it 4.5 degrees of freedom, in the sense that they do very well on angle and displacement, but they have a rather slow F number, and so focus is somewhat soft. If you use a rotary table, you can probe what you're trying to center with mechanical indicators, but then that assumes that the what you're probing is mechanically perfect. Also, probing 2 points along the optical axis obviously gives you 4 degrees of freedom, but you still need an optical instrument to pick up centers of curvature of your system. And this comes up with our second polling question about how many of you have used an autostigmatic microscope, because this is the instrument I'm going to talk about for most of the rest of the talk in terms of using it to sense the Bessel beam, and also to help produce a Bessel beam along with what I call an axicon grating. And again, you know, I've gone over some of this initial stuff because using the Bessel beams kind of goes counter to almost everything you've learned in sort of classical optics. So yeah, it looks like about half of you have used an autostigmatic microscope. So that's we're in good shape there. So this is a picture of an autostigmatic microscope. We use a point source of light as opposed to an ordinary microscope where you would have a full field illumination. We just use a point source of light. It's collimated, comes down through a beam splitter and out through a microscope objective. Since it is collimated space in here, if you took the microscope objective off, the autostigmatic microscope would behave as though it were an autocollimator. With a spherical surface out in front of the microscope objective, if the objective is focused at the ball's center of curvature, the ball acts like a convex mirror. The light goes right back into the microscope, and a tube lens focuses the light on a CCD array. If the ball is perfectly centered with respect to the focus, then the point source of light here is exactly conjugate to the center of the camera screen. If the ball's decentered, you'll see that spot move off the center of the screen. Whoops. Now, the other instrument, of course, that's classically used is an alignment telescope. They're beautiful instruments and been around a long time, but they're also a bit complex and tedious to use in the sense that you've got to pick up two centers of curvature to do alignment, which means you've got to keep focusing between one center of curvature and the other while you're correcting alignment. So now we'll get into the matter of people looking for better approaches to alignment. And McLeod at Kodak invented what he called the Axicon, which is a cone-shaped lens. What happens with the Axicon, you've got it illuminated with collimated light. If the light or the light rays that come in close to the axis end up interfering close to the Axicon, while rays coming in toward the edge interfere farther away, and you get this line of bright objects. It varies in intensity, but it's a continuous line along the axis of the Axicon. It's interesting, in McLeod's paper, he has a diagram that's almost identical to a paper by Durnan, who is the person who first identified Bessel beams in a JOSA article in 1987. Also, McLeod refers to work by Van Heel. It was even easier, even earlier, where he used a grating to create a beam for alignment that was like the Axicon. I should point out here too, McLeod's picture shows a mirror with a pinhole in it so that it can both illuminate the Axicon and view the light coming back from it. If he'd had a point source microscope or autostigmatic microscope, he would not have needed the pinhole mirror. So this is some work by Van Heel. He used a grating where he used lines that were spaced about 1 millimeter apart, actually ground the surface of glass to get the grating. When it was illuminated, he got this sort of picture with a bright core in the middle. His intensity pattern looked really very similar to what was published by Durnan, showing what the intensity pattern of a Bessel beam would look like, although neither McLeod nor Van Heel referred to their work as Bessel beams. So shortly after Durnan talked about creating a Bessel beam with an annulus, or a mask that let through an annulus of light, these Finnish people, Turnen et al., talked about creating a Bessel beam using a grating. And I've done similar work getting gratings made by Arizona Optical Metrology that had about 10 micron spacing between the concentric circles. And this is just a micro photograph of the grating I used. And then in this little video clip, you'll see the point of light that's really the core of the Bessel beam. There's some fringes maybe very faintly shown here. But as I run the video, you'll see the spot moving around because I'm looking at the Bessel beam as my microscope is moving along a slide, and so the spot there is moving because the slide is not perfectly straight. To give an idea for dimensions here, it's about 11 microns between the inner points of the star here. So to talk a little bit more now about the Bessel beam, I've got a grating down here. It's illuminated by a point source of light. So you've got a spherical wavefront illuminating the grating. Comes on up this continuous line of light into an autostigmatic or point source microscope.
Bob, excuse me, Bob, I apologize for interrupting. If you are using your cursor, we're not seeing it on the screen. Ah, there it is. It was there a moment, and now it moved away.
Oh,
there it is.
You see it now?
We see it now. Thank you.
Okay. Okay, again, point source of light, spherical wavefront, autostigmatic microscope. This is the Bessel beam. You see the bright core and the rings around it. What I've done here is to illustrate that the microscope doesn't have to be at any particular conjugate of the lens, but if you put lens in here, in this case, I've got a negative lens. The core is still there. It changes the spacing of the rings, but I've not moved the height of the point source microscope at all. I have centered the lens as well as possible, so I get the spot in the middle of the crosshair. And here, again, not moving the microscope at all, I've just substituted on this seat a positive lens. Again, the rings change, but that is the only thing that's different. Now I'd like to show actually centering lens on a seat with the microscope. Here, just to get a simple support for the system, I've got a meniscus lens here, and I'm pretending that I'm using it as the seat while I put the positive element of the meniscus on top of this. And so here's the video of this operation. You can see, even though the core of the beam is way off the screen, you've got rings from the Bessel beam that tell you which way to the lens to bring the Bessel beam onto the crosshairs. I've got a slide coming up that will show you what's going on in this part of the screen to show you numbers here of the number of microns the spot is from the center of the crosshair. I'm going to run this again, so just to give you a better feel, you can see the rings when the beam is outside the field of view. The fact that they get dim here is the software set up with an automatic gain control to keep the brightest pixels just under saturation, so the image doesn't get distorted because of saturation. On the other hand, when the bright core is outside the field of view, the gain is turned up so that you can see the rings around the core of the Bessel beam. So this operation took about 45 seconds. The microscope was about 20 millimeters above the lens. And so if you convert that to angle, when you got the lens centered to a micron, that's about 10 seconds of arc in terms of angular centering. This is a screen, and let's see if that video will work. Yeah, you can see the numbers here of how far the spot is from the central crosshair. You can also see how the shutter speed changes as the spot is brought, so the core of the spot's in the field of view. The units here are in microns. The distance the spot is from the crosshair on the microscope. And that, then we get to the number 3 poll question. And I just wanted to ask about using vacuum, because in the picture there, I was using vacuum to hold the lens in place, the lower lens, while we centered the upper one. And I just wanted to point out, a lot of people don't use vacuum, but I have always found vacuum is a very nice thing to use along with optics, a very nice way of holding things down. And so when I see a majority of the attendees have used vacuum, so they are familiar with that technique. Okay, now I want to go into the question here of centering the seat that the lens is on, because if the lens is on a seat, then the center of curvature of the side of the lens that's on the seat is always going to be on the axis of the seat. And of course, you need the axis of the seat centered on the Bessel beam, as well as the second surface of the lens, to have the lens centered both in decenter and in terms of angle. So what you do here is set the microscope at the center of curvature of the concave side of the lens, and simply put the lens in there to make sure you are at that height. Then remove the lens and make sure the microscope is centered in both X and Y on the Bessel beam. Then you put the lens back in and do a combination of both centering the seat and rotating the lens in the seat. And in this case, you will see 2 spots in the microscope. One, the transmitted beam through the lens, and the other spot, the reflection from the center of curvature. To get the lens perfectly centered in terms of tilt and decenter, both spots must converge on the crosshair on the microscope. And in that case, then you know that the lens is centered free of tilt and decenter. Now we've got a little video that shows this operation. What I'm doing here is with the screw centering the seat. The reason I asked about vacuum, this chuck here is held down to this glass plate. Here we're adjusting the centering of the seat a little bit, but the chuck is held down with this black line here, vacuum to the glass, while this line here is vacuum in the core of the seat, or the seat to hold the lens down while we're doing the adjustment. So let me show this again. We're simultaneously bringing both this spot from the center of curvature of the upper surface, this spot of the transmitted Bessel beam through the lens, and we've got to get them both on the spot. Well, this looks a little complex. Once the seat is centered, you turn up full vacuum and you never have to adjust the seat again because you know it's centered. And then you can do any other centering operations just one after the other because you know the seat is centered. Now, let's see. Now, this slide is to show that once the seat is centered, how quickly you can put another lens on the seat and get it centered again. So here I'm picking up a lens, centering it on there. You've got the rings to know which way to bring it into centering. Since the seat is centered, we still have the two rings because I haven't moved the microscope. And so we're still seeing the center of curvature of the concave side. If instead I had said, okay, the seat is centered, I just want to center the lens, I could have moved the microscope up to, say, 200 millimeters from the lens. And then if I had the lens centered as it's shown in this case to about a micron, my sensitivity and tilt would have been that I have the lens centered to 1 second apart, which it's more than typically needed for most lens systems, but it gives you an idea that you do have this sort of sensitivity when you use the Bessel beam, because the beam goes through the optic as though it were a single ray in a ray trace program. And so anytime you put a dummy surface in your ray trace program to see where the coordinates of the beam are, you do the same thing here in real experimental practice instead of theory. And you can see in any plane along the axis of the lens where that beam is coming out. And so in practice, if you can see the two spots, you can tell where the beam is as well as what the angle of the beam is. So that's pretty much what I've got to say about using Bessel beams. As I said, it's kind of new to wrap your head around. On the other hand, I think it's an extremely powerful technique for centering optics, and really doing this talk to make this idea of using Bessel beams a little bit more widely shared. And as I say, it's simple to create the beam. All you need is a grating and a point source of light. Again, people think of using Axicons with collimated beams. You don't need to. End of a single mode fiber works just great. You can interrogate them anywhere along. I've gone out 30 feet from the grating and you can still see the beam. Because you can set up a situation where you have the two spots of light, you can do the centering, both decenter and tilt, without the need of a rotary table. And again, I just use cementing of a doublet there as a very simple example, because if I tried to show centering lenses down in a tube, you can't really see anything that's going on. And so the example with the doublet gave a very simple sort of scheme to demonstrate the idea and yet be exposed enough that we could actually make a video of what was going on. So that's pretty much what I've got to say, and I'm open for questions. I appreciate all of you signing up to listen to this, and I'd be glad to take questions.
Okay, thank you, Bob, for the interesting talk. There were a couple of questions posted in the Q&A while you were talking. The first one, the question is from Jose Sacian. I hope I pronounced that correctly. The question is how the Bessel beam compares to using a laser beam instead.
Oh, great question. About the smallest diameter you can make laser beam is on the order of 3 millimeters. For the gratings, I was using with a 10 micron spacing, gives you a diffraction angle of about 1.8 degrees, but the core or full width half max then of that beam is about 7 microns. So it's orders of magnitude smaller in diameter than a Bessel beam.
Okay, thanks, Bob. There's another question here from Cynthia de la Rosa. Question is, do you see a benefit to also placing the seat and the lens on a rotational stage along with using vacuum and a PSM?
So say that again. I didn't fully.
Do you see a benefit to also placing the seat and the lens on a rotational stage along with using vacuum and a PSM?
Oh, well, certainly I would say yes. There are certainly situations where a rotary table is still beneficial in your alignment. Probably putting lenses in a barrel, the rotary table gives you a good opportunity to center the cell in the first place. On the other hand, the rotary table's not the only thing you can use for centering the cell. Sometimes the dimensions are appropriate to simply put a ball in your cell and use the microscope to find the center of the ball to seat the or to center the cell in the first place. I'm not saying don't use rotary tables. I'm just saying there is an alternative that is often simpler. And from my own personal experience, both using a rotary table and just the Axicon grating by itself, it's much faster and less tedious to do the centering using the grating and as opposed to using rotary table.
Okay, thank you, Cynthia, for the question. The next question, Bob, is from Costa Falagis. What would be a good apex angle for the Axicon?
Oh, I think it depends on situation. I've simply found that, and I simply pulled this number out of the air, the 10 microns that I made my gratings. It's worked well enough that I've not found a situation yet where I wish I'd used a different spacing. So a roughly 2-degree angle of the beam coming off either the axicon or the grating seems to work well. I would say too, if you're using an axicon, again, you can illuminate it with a point source rather than a collimated beam and get exactly the same effect. I think the nice part of using the grating is that it's made by photomask e-beam techniques, and so it's essentially perfect without having to try very hard. But rotary tables, there is a bit of a problem there getting your vacuum in, because you usually need a rotary connection that's going to obscure the axis, unless it's an air-bearing type table where you can bring the vacuum in through channels around the axis of the table. I hope I've answered that there.
Thanks, Bob. Another question. How do you align the axicon to the single mode fiber beam?
Good question. This is where the point source microscope comes in, because what you want to do initially is use the bright spot at the focus of the point source microscope as your point source to illuminate the grating. Then when you see that spot reflected from the grating in the center of the crosshairs, you know that the focus of the microscope is on the line that also is normal to the grating at the center of the pattern. Then you can put your point source with a fiber on the opposite side of the grating used in transmission, and move the fiber around until, again, it is centered on the crosshair. Then you know that the point source in transmission is exactly on the axis of the grating. You can also be misaligned with respect to the grating and still get a perfectly good Bessel beam, as long as you're within a degree or so of being aligned perpendicular to the grating.
Okay, lots of good questions. I don't see any more posted, Bob. However, I think we have a couple more minutes in case there are other questions coming in. And I wonder if if you wouldn't, maybe if you could share a little bit about Optical Perspectives Group and what kind of consulting your company does, just for the audience here.
Yeah, I'd be glad to, but one thing I'd given to Katina to potentially for you to ask was why I think alignment's important in the first place, and why I wanted to give this talk. And that's because you've got, with computers and these lens design programs, the ability to design essentially perfect lenses. Given the field of view and the materials and all that, whether you're using Code 5 or ZMAX or some other program, each program converges on the same sort of design, which is essentially perfect for that task. And then you go to your optics shop, and through computer control polishing, the beautiful software and all for the interferometers, you can make essentially perfect optical components. And so alignment is the only place left to improve your overall system performance, the alignment lets you get these perfectly designed, perfectly manufactured components put together so you're getting absolutely the most performance out of your optical system. And this is why I think why I think alignment is important, and it's been sort of overlooked as sort of the last element in essentially making perfect optical instruments.
Okay, there's another question posted here, Bob. It's from Scott Stewart. Thanks. I have trouble imaging. How would I use this with a series of reflective elements?
Well, that's the next thing I want to work on. I have built a crude, what I call Bessel beam projector, and you've got to, yeah, things work out fine in transmission because nothing's in the way of the microscope looking at the beam coming back. But to do reflecting optics, you've got to get the Bessel beam in and pointed toward the reflecting optic out in front of the microscope objective. And so you need a set of optics in front of the microscope objective to do this. Anybody that's interested in this, I have written a paper on what happens when you do try and use the Bessel beam reflecting optics. And it does work. It's just I haven't gotten far enough downstream to implement this Bessel beam projector so that it's a practical thing to use for aligning reflecting optics. Scott may have asked the question because of people who want to build infrared systems. You've got things like germanium and silicon that don't transmit into visible. Yet, if the seat is lined up, then you could align the germanium or silicon in reflection to get rid of the tilt and essentially have a perfect alignment, even though you're not transmitting through the element.
Bob, how did you first become interested in Bessel beams for optical alignment?
Yeah, this goes back to when I was working with Jim Burge at the university. One of his, well, Jim's always been very involved in using holograms for optical testing of A-spheres. And of course, in order to do your CGH correctly for doing an A-sphere, you've got to get it aligned relative to the interferometer very precisely. And mechanical attempts to do this got you close, but not quite where you wanted to be. And so Jim had one of his students, Laura Coyle, put Fresnel zones on the CGH, where the Fresnel zone focused at the center of curvature of a ball. And so she was able to cement balls onto the CGH using an instrument she designed, but it was essentially an autostigmatic microscope, so that it would focus at the center of the Fresnel zone, and then you could slide the ball in so that its center lined up with the focus of the microscope. And I appreciated how nicely that worked and thought, well, I wonder if you could use this for cementing doublets, and designed a CGH where you could first get the meniscus element in there, and then put the positive element on without having to move the microscope. And did this by making two concentric Fresnel zones with different radii of curvature. And that whole experiment worked out just fine. So then, but the drawback was that you had to have a different hologram or Fresnel zone pattern for every different design doublet that you wanted to cement. And I got to thinking, is there a universal way of doing this? And I'm not sure what it was that actually triggered the idea of Bessel beam, other than I was already familiar with the idea of the Fresnel zones and concentric Fresnel zones. I don't know whether I just said, geez, I wonder what would happen if you simply put down a pattern of concentric, evenly spaced circles, or whether I knew enough about Bessel beam generation to begin with that I had a clue of how to start. But I'm basically an experimentalist at heart, and I may have just said, make me a grating with concentric circles and let me see what happens. But it certainly worked out the way I had hoped it would, and I'm grateful to Arizona Optical Metrology as part of Optics Valley for being able to make gratings for me. And I should say too, I'm again grateful to Optics Valley companies in terms of optical support who actually build the point source microscope for me. So I hope that gives you a little idea.
Yeah, thanks for the background. Appreciate that, Bob. I think we have time for one more question. It's from Robert Schroeder. The question is there a difference in the alignment of A-spheres versus spherical surfaces with Bessel beams?
I don't know. I mean, to first order, alignment is a paraxial effect. And so whether it's A-sphere or just spherical surfaces, it doesn't make any difference. I do know, though, if you've got an A-sphere and its axis doesn't go through the center of curvature of spherical surface on the other side of the lens, you've got a problem. And I also know that Bessel beams going through say decentered, where you put astigmatism in the beam, then the Bessel beam tends to blow up, become sort of a diamond-shaped pattern. And again, there's, I would say, tons of work for somebody that wants to investigate this farther. But to give a clear answer to Robert's question, I'd have to say I don't know. That's for future work.
Okay. Well, Bob, I think that's the time we have. Thank you again for a really interesting talk, and clearly lots of good questions and discussion at the end. So thank you again for joining us on the webinar series.
You're very welcome.
And at this point, I'll hand over to Jack to close out the webinar.
Thank you, Robert, and thank you, Bob. Excellent presentation. Hey, one comment that really stuck with me, and you were very positive about it, but very low key. Simply saying, give me perfect components, but make sure you use perfect alignment. And I always have a more negative attitude, which is, if you don't have good alignment, you can mess up the best components. Bob, thank you. Great presentation. We also want to thank our webinar team, Robert and Katina. Great job as usual. We will be making available recordings of this webinar by Friday. You will hear about it by email, where to find it, and so on. A couple of other upcoming events to note. For our Optics Valley members, we have a general member meeting at the Loft on the 12th in the afternoon. Very interesting program, don't miss it. And we will finish with happy hour. Another of these technical series webinars is lined up with Michael Hart from Hartside on October the 5th. And then please don't forget our local exhibition effort under the auspices of the Arizona Technology Council, the annual Business Expo, Tech and Business Expo at the Tucson Convention Center. And before I say just a couple of words about the Arizona Photonics Days, let me also just leak a time in point that we're working on, which is on the 15th of December. We're hoping to invite for a special event in recognition of the International Year of Glass. Please stand by for announcements, hopefully in the next few days. And then at this point, we're obviously moving up towards our Arizona Photonics Days, the 6th time in Tucson. For those of you coming from overseas, very easy to approach Photonics West and San Francisco by going through beautiful Tucson with beautiful weather year-round. The 5 tracks are very much the same as last year. We are open for papers. Please submit your papers by November 1st. And always happy to talk to you about being a sponsor. Hope to see you all in January for that event. Now, one final point before you sign off today, please spend a couple of minutes to answer a few questions in our mini survey. That helps us to further improve our seminar series. And thank you all for joining us. You now have about half an hour to get over to the Apple event and the new phones and watches. All the best. Be well.